Hi everyone, thank you and welcome to everyone, both the people who are in the room with us today, people who are online, and of course the people who will be watching the recording in the future. Today we've got David Bamman with us, who is an associate professor in the School of Information at UC Berkeley, where he works in the areas of natural language processing and cultural analytics, applying NLP and machine learning to empirical questions in the humanities and social sciences. His research focuses on improving the performance of NLP for underserved domains like literature, and exploring the affordances of empirical methods for the study of literature and culture. He's got a PhD from the School of Computer Science at Carnegie Mellon University, and he was a senior researcher on the Perseus project at Tufts University, which I'm sure you're all really aware of. I'm personally a huge fan of that particular project. Today, David's going to talk to us about Latin BERT, which is a contextual language model for the Latin language. He's going to present a series of case studies for its use, and also illustrate some other uses of this language model, both for the work in natural language processing for Latin and for traditional scholarship. So thank you, David.
Great, thank you, Megan. Thank you, all of you, for having me here too. I've been wanting to come and talk about this work on Latin BERT for a while now, so I'm really glad to have this opportunity to be here and put it up in front of you all. I would love to get your feedback too on the kind of philological uses that you might have for this as well. Right? I mean, my own background is as a student of classics. In my early life, I've since moved not on, but added computer science and information science to that. But you're really the ones with the philological expertise, and I would love to understand more of what we can do with these kind of contextual models. But what I will present at least are a couple of case studies for illustrating what we can at least do in theory with these models for learning about the classical world. I'll mention too that this work is in collaboration with Patrick Burns, who's at ISA now at NYU, with support from the National Endowment for the Humanities. On Patrick's side too, I'll mention that he just recently came out with a new model for Latin for Spacey called Latin C. So I encourage everyone to go out and look at that. It's really a fabulous set of tools out there too. Okay, so this talk is really one about contextual language models, right? That is what Latin BERT is. It's a contextual language model. And I think at this point, I would guess that probably everybody in this room and everybody who is watching this on YouTube right now has at least some exposure to language models, right? Either from being in the general digital humanities community and seeing BERT on your radar for the past 5 years. Maybe you've seen some of these other models like Roberta, Longformer, Claude, Palm, OPT, Bloom, Llama. But if you haven't, you probably have at least seen the public uproar over the past 6 months from ChatGPT. Right? ChatGPT, GPT-3, GPT-4, these other class of models from OpenAI that are essentially all just contextual language models, right? So everyone at least is exposed to these kind of ideas increasingly over the past 6 months, but they've been around for a long time. Before getting into Latin BERT, what I want to do first is just talk about two of the really important components of these contextual language models. One is their status as language models. Right, being models that are designed to predict the probability of a word, and thereby the probability of a sentence that you can then use for doing a lot of NLP things, and have been used for a lot of NLP things for the past 40 years. So one is their status as language models, the other is their status as contextual language models. And that's really what makes Latin BERT and all of these models that we see right here different from other kinds of representations for words that you might already be familiar with, like words of right? Words of and glove, these other static representations of word meaning that we can see as being non-contextual. But first we can start out with this idea of these models being language models at all in the first place. Right? What language models are really just machinery for calculating the probability of some sequence, right? Now, these are old devices. They've been around for the past 40 years at least. They were really an intrinsic part of early work in natural language processing for machine translation, for speech recognition. They currently are for optical character recognition, right? They essentially give us a way to assign a probability to a sentence. So if you have a model like machine translation, where there are two different translations that might have equal fidelity to the source, if we have a way of parameterizing which of those sentences are more likely to exist within the language, right, by calculating a probability from them, we have some other information that we can use to prefer one translation over another. Right, so all language models are effectively models to calculate these kinds of probabilities. How likely a sequence is to exist within a language. And more recently, this involves components for predicting the probability of individual words within those sentences. Now, all language models are really designed to predict missing words from a sentence. So to give you an example here in the context of BERT, it's based on a transformer architecture, but that's not really critical to any of what I'm talking about today. You can pretty much do any of this same kind of work with LSTM type models, with other neural models. You can do it with non-neural models like logistic regression as well. The core here is this framing of masked language modeling as being the machinery by which these models learn the probabilities of words and sentences. And the idea behind that is that if we have a sentence like the dog barked, what we're going to do is wrap it in some artificial tags, the start token, CLS, the end token of a sentence, set right here. And what we're going to do is mask out one word from this sentence and try to predict it. Right? We know the truth. We know this word should be dog. So what we're going to do is observe that word and tune all of these parameters in this model so that when we see the blank barked, we're going to predict dog with high probability. Right? So now this illustrates that we don't need to have any human annotations for this. Right? You don't need to have a person sit down with a bunch of documents and label what the correct word is in a missing context. That just comes to us from the structure of language. Right? Any really large document collection, you can learn these kind of models from. So we can do this with dog, masking out that word. We can do it with another random word from the same sentence in a different iteration. Right? So the dog blanked. What is the word? In this particular sentence, we see it was the word bark. So we're going to try to encourage our model to be able to predict this word bark by changing all of those weights, changing all the parameters of the model to be optimized to make this prediction data. Now, in this kind of view here, what this is doing is giving us a model that can predict the probability of a word, but as a byproduct, it's also giving us a representation for every single word in the sentence that we're using to predict those missing words. Now, in this kind of view here, what we're doing is using the context that a word shows up in to learn the representations for each of the words within it. Now, in this kind of view, this is, in that same kind of philosophical paradigm as all of lexical semantics that, whenever you see these kind of talks in digital humanities or NLP, you probably have seen a sentence like this from John Coper's from 1957. You shall know a word that the company keeps, as embodying the kind of philosophy that's guiding how these words are learning those representations. But this work goes back much earlier, or not much earlier, but earlier than Firth's work as well. So Zelig-Harris famously had a lot of very similar studies looking at morphological structure, the distributional properties of morphology, a couple of years before John Firth. Zelig-Harris is famous not only for being, for his own work on linguistic structure, but also for being the advisor for Noam Chomsky, who's very famously anti-empirical, this use of data to learn these kind of distributional properties. But also, of course, this philosophy goes back to work like Wittgenstein as well. Right, this idea that meaning is determined by use, right? We could think about, enumerating the meaning of the word fork by just describing or identifying every single fork that exists as being the denotational meaning of this word, but it's also really known to us by what we use it for, right? We use a fork to eat food. A fork is often given for wedding gifts and so on. Right, the meaning of a word is not just its denotation, but also the general context that it appears in the other sentences by which real people are using it to do things with language. So these kind of models have been around for a long time. Right? People have been training language models to predict the probability of words in a sentence in order to embed them in models for speech recognition, for machine translation, for object character recognition. What's relatively new or impressive about recent models is that they can generalize much beyond the data that they've been simply trained on. Right? So if we were to learn a language model on some collection of text, a traditional language model might struggle to fill in the blank right here, right, from Orwell's 1984. Right? It was a bright, cold day in April, and the blank were striking 13. Right? What strikes 13 is very rare for anything to strike 13. But here, if you look at a collection of literary texts where we see the word clock and the word striking, you can see how there might be structure that a model can learn what the correct term is to fill in this blank. Right, the correct term is clock. Looking at data, we see clock strike 2, they strike 12, they strike midnight, they strike 8, strike 4, strike 3, strike 11. They strike numbers, right? Not necessarily numbers from 1 through 12 like we might be used to, but also numbers like 13 in this futuristic or dystopian context. So we've also seen how these kind of models, when we train them on a lot of data in models that tend to be really highly parameterized, right? When having a lot of numbers that we learn as a function of this mass language modeling objective, end up recreating a lot of the natural language processing pipeline. Because if you want to use a model to infer the syntactic structure of a sentence, or to infer the semantic structure, the part of speech is the parts of speech of the individual words. For a language model that only observes words and none of that explicit structure, you often need to be able to understand that latent structure of language to be able to do those things. So from any of this work that has essentially probed what these models learn and where in their parameters they've learned them, what we found is that low-level information shows up early on in these models' layers, and higher order information about syntax, about semantics, about discourse, like co-reference, tends to emerge later on in the upper layers. So a lot of this work here uses language modeling as a kind of foundation for higher order things because natural language implicitly encodes those things that we can think about extracting from the parameters of these models. Now, at the same time, people have found that when we train these models on really large collections of data and have the capacity for memorizing aspects of those training data, aspects of that training data, language models are really great at encoding knowledge that is directly present in the training corpus. So there's a sense in which we can transform a lot of tasks in NLP to being just language modeling tasks. Right, we can say, well, the director of 2000, instead of asking, who's the director of 2001 A Space Odyssey, right, as a question, we could just treat this as a language modeling problem and say, the director of 2001 A Space Odyssey is fill in the blank. Right? It's a predictive problem that just predicts what that single next word is. Right? We can do this for question answering type of problems like this. We can think about doing this for machine translation as well. Right? So the French translation of cheese is fill in the blank. What is the next word? Or even of other tasks like sentiment analysis. Right? Given enough context, right, enough of the document that you want to infer the sentiment of in the prompt, we can simply say the sentiment of the document is fill in the blank. Right? And a lot of work here, especially with the GPT class of models, tends to do this really well in this zero-shot scenario. Right? When we don't provide any kind of training data at all, but just prompt the model to give us an answer where that answer is designed as a language modeling kind of task. Right? So work that has examined this in the context of Wikipedia, right, a BERT that's been trained on Wikipedia and some fiction, has verified the kind of information that tends to be memorized by these models. Right? So if you prompt BERT, for example, to say, Francesco Bartolomeo Conti was born in fill in the blank, it will predict Florence as being the next word in that sentence. It's not the correct answer, but it is the second, it is only second worst, all right? The second most probable token among the generations here, right? Adolf Adam died in fill in the blank. It predicts Paris. Paris is the true answer. So in all these contexts here, we can see how the training data is essentially being encoded in the parameters of these models. These models are effectively compressing the training data into those weights. Right? From a philological perspective too, we might think about how we could exploit this principle here for doing things with these contextual language models. So the other important context here is that all of these models are not just language models, but they're contextual language models, which means that we have a representation for every token in context and not just for every word as it exists in some vocabulary. So this is very different from word to vec. or GLOVE, right, or other earlier models for representation learning that's been exploiting this distributional hypothesis that's encoded in this, you will know a word by the company we keep, aphorism from John, right? Because in Word2Vec and in GLOVE, right, effectively what we get out of those models is a big matrix that looks like this, right, where the rows are all of the words in your vocabulary, and the columns are all of the different hidden dimensions, the different dimensions of the representation for those individual words. Importantly here, we have one row for every word as it exists in your vocabulary. So every time you see the word the, you're going to look up this embedding, and that's going to be your representation for that word. Now, we've seen from this earlier work on representation learning how you can take these high-dimensional vectors, use some dimensionality reduction method like t-SNE or even PCA to reduce them to, let's say, 2 dimensions, that we could plot them on a graph like this. And what we find is that words that have similarity in meaning also end up having similarity in their representation by virtue of the distributional hypothesis, which means that words like dog end up being close to words like wolf and close to words like bear, very far away from other words like wrench and screwdriver. The problem though for this, and again, this is really where it becomes important to differentiate this core concept, especially as you see it being epitomized in the digital humanities between types and tokens. Because what Word2Vec and GLOVE learn is a representation for a word type, the word bear. It doesn't learn representations for word tokens like we might see in instances or instantiations of that vocabulary word in actual sentences. So the bears ate honey, bears there was a token, we spotted the bears from the highway, Yosemite has brown bears, the Chicago Bears didn't make the playoffs. Right? All of these are tokens, right, of the word bears, which is itself a word type. If we were to use Word2Vec or GLOVE, right, these static representations to encode the meaning of the word bears here, we look them up, no matter which of these token uses, we're going to have exactly the same representation. Right, this is a problem for this kind of work of having any kind of context sensitivity. Right, what we want to have from these models is the ability of saying, for a given token of the word bears, Yosemite has brown bears. That might be very close to the representation that we would learn for the word moose in We Saw Moose in Alaska. And both of those would be very different from a different token of the word bears, like the bears lost again, which itself might be close to other words that have ambiguity of meaning, like go pack go. Both Bears and Packers are football teams in the US, have very different senses from bears being used to describe an animal. So with contextual language models, we can do this, right? We have different vectors, right? Different lists of numbers that describe these individual instances of the word bear. So since their introduction, right? Since this big pivot in NLP to focus a lot on the use of contextual language models, we've seen the state of the art for just about every task in NLP go up dramatically, just by virtue of swapping out either neural models, non-neural models with neural models at all, or even switching out static Word2Vec embeddings, representations of words, with these context-sensitive ones, right? So that's true for NER, for syntactic parsing, for word sense disambiguation, which for a long time struggled to get beyond the most frequent sense baseline for words. We actually start seeing some progress being made with this task. For co-reference resolution and for natural language inference as well. Just using these kind of contextual language models really dramatically improves the performance, right, in a way that I don't think people would have anticipated 10 years ago. But the question here is how we can think about the use of these kinds of models for traditional questions in classical philology, right? We can think about them effectively as being forms of representations for the meanings of individual words, but also providing us with at least some kind of learned machinery for algorithmic measuring devices that we might want to tune for specific tasks in philology. Right? People have already thought about the use of static vectors for uncovering intertextuality and elusive texture use, for modeling word meanings in philosophical texts and Neo-Latin texts in particular, and also for using word embeddings to study semantic variation in Homeric formulae in particular. So when we look at what kind of models exist, right, that are in these kind of contextual language model space, Hugging Face is a fantastic repository for a lot of these kind of trained models. You can go there, get trained models for English, for Russian, for Spanish, for Italian. If you look at the University of Berkeley, also has a great index to a number of different contextual language models, along with reports for how good those models are for individual tasks in NLP. Right, so a lot of contextual language models exist at this point that people have been using to raise the state of the art for a number of different problems and tasks in NLP more in general. But there isn't one for Latin. There isn't one, there hasn't been one historically for any classical language. Since then, there have been a number that have been developed for ancient Greek as well. But this did the lack of any model for Latin really did motivate us to develop a language model for Latin that has the same kind of context sensitivity. Because again, we can think about how we might really be able to train these models relatively easily conceptually. Right? That when we take a sentence like "Nova Ferganus mutatis digere blank corpora," right? This task of mass language modeling is really just to take this sentence where we know what the blank word is and train a model to predict exactly that word in the context of this Latin sentence and not just in English or the other languages that we've seen these kind of models being trained for. But the hard part here is where we get enough data to be able to train a language model that has this kind of context sensitivity. Because it's relatively easy to train a smaller static word-to-vec style model on a smaller amount of data and still have it work relatively well. But these contextual language models tend to demand a much bigger collection of data. So to do this, what we did was went out and found as much Latin as we could. Right, both clean Latin, as it comes from human eyes on text that has really focused a lot on the philological practice and making sure those words are the correct ones in context. So we gather data from the Corpus right, the works of Thomas Aquinas, the Latin Library, we gathered from the Pagina Latina, from Latin Wikipedia, which has a lot of articles in Latin about Beyonce, about Barack Obama, right, not in a historical context. And we also gathered most of our data from the Internet Archive, right, which contains a lot of different versions of traditional classical texts, but not just classical text, works from medieval texts as well, Neo-Latin texts, from all of those 19th century German dissertations that are written in Latin. You can find many of them in the Internet Archive as well. So in total, we have a collection here of a data set that spans 642 million tokens, right? It covers many different copies of the same work in different forms from the Internet Archive. We tokenized, right, we took these documents and divided them into sentences and divided each sentence into words using the CLTK tokenizer, right, one that has been developed specifically for Latin. And because these models tend to use a smaller representation of words beyond entire tokens, we also learned a word piece subtokenizer as well from this collection of data. So what a word piece tokenizer does is take a word like outperforms and break it up into smaller pieces, right? So that we have a vocabulary size that's not on the order of millions of words, as we might have from a even a classical Latin vocabulary where we know that there aren't any OCR errors into it, down to a vocabulary size that's about 30,000. So we have audent as being a word that exists within this vocabulary, es as being a word as well. Now, in some cases, this tends to correspond to what we might think about as morphemes or morphological distinctions, but not exactly, right? It really is capturing simple regularities as they exist among the characters in this particular collection of data. So from this collection of documents, using this tokenizer, along with the word piece tokenizer that we learned on this collection of data, we then trained a base BERT model that has 12 layers, 768 numbers for each individual word that we're passing through this model, and train it for 1 million steps, which costs about $540 on Google Cloud using their TPUs. Right, so not exorbitantly expensive, one that can be done within a research budget. Right, not on the order of the millions of dollars that it costs to train contemporary GPT style. So I mentioned the Internet Archive here as having one place where we have a large collection of data that is used to train this model. The Internet Archive has a lot of variability in terms of the quality of the data within it, right? In terms of the OCR in particular, right? So that you often have text that look like this, right? Relatively good Latin in terms of its form, but also text that look like this, right? Where it's clear it's been, there's been some language identification problem that it hasn't been recognized as Latin at all. Or maybe that it's in a script that simply can't be read. Right? You can, maybe if you squint your eyes, you can see some forms that look a little bit like Latin, but really it's not that great. So to be able to filter out these texts, but still make the most of this collection, what we did was remove all text that where at least 40% of those words in that document weren't recognized in the vocabulary learned from the non-OCR text. So from the Latin library, from the Index Themysticus, to make sure that these words that we were using from these documents actually correspond to what we might think about as being Latin. So the task then is really just the same, right? It's a mass language modeling objective where we pass a Latin sentence through this BERT model, right, through this transformer, to then take that one word that we've masked out to predict its identity. So when we're pair blank envelope, we would predict the word beyond here if that was the word that we see within that original sentence. And we can do the same thing in the context of even OCR errors, right? So what we're trying to predict is the word beyond, but we see some words that have been corrupted by OCR mistakes. We're still burdened by using that really noisy data to make predictions about that word whose truth we know. So in a sense, this gives us at least some capacity for learning robust models of language that can be robust, right? Not sensitive to those kind of OCR errors that exist within those documents that we're training from, which can be useful for some tasks. Okay, so let's talk about some of these case studies that we ran on using this Latin model, right? One of them we could think about was the degree to which we see information at a higher level being directly encoded within those representations for those words without doing any training at all. So one of the first things that we did here was just do a dimensionality reduction on around 400 different instances of the word cum in the Index Themysticum, where we know that each of those instances of cum is either a preposition, so an ADP in their terminology, or a subordinating conjunction, right, an S-conj, as they use it, right? So cum can either be a preposition, right, it takes a noun in the ablative case, or it can be a subordinating conjunction, meaning because or since, that you see being used in very different contexts. Now, if we take all of these 400 sentences, run them through Latin BERT, and then reduce the dimensionality of those vectors corresponding to those 400 instances of the word cum, plot them down, reduce them down to 2 dimensions, and plot them like this. What we can see is a natural distinction between the prepositions and the subordinate conjunctions. Right? This to me was astounding. Right? We didn't train a model to predict whether a given instance of cum was a preposition or subordinate conjunction. This is not the task of POS tagging yet. Right? It's just looking at the representations we have for these words and see if it naturally aligns with this distinction between prepositions and subordinating conjunctions, and it does. Right? And the kind of mistakes that it makes, we can see natural explanations for. Right? So in the lower right corner there, that word is truly a preposition, but it's used immediately before the word talk. Right, which could be a nominative, accusative, an ablative term, so it's natural for it to be confused and think that it is a subordinating conjunction, or in that context. And likewise, in the example at the top right, we see that word, the blue dot there is truly a subordinating conjunction, but there we see it again, immediately before an example here with octu, that again, coerces the model into thinking that it might be a preposition belonging to the rest of that class. So, but we also trained the model to examine, right, to treat it as a benchmark and compare with other models that have tried to carry out this task of POS tagging by training a model natively for the task of predicting the part of speech of a word, right? To take a word, to take a sentence and identify whether a word is a noun, a verb, an adjective, and so on. Taking our model fine-tuning it for these different data sets for the Perseus tree bank collection, Proyel, and the Unix Mysticus tree bank, we see Latin BERT really yielding a state-of-the-art for this task of part-of-speech tagging, again, by having a representation for all of those words that is now sensitive to the context in which we see those words being used. Right, beating other versions that also use other kind of contextual language models like multilingual BERT, and also beating a model that we tried that was just using word-to-vec style representations embedded within a bidirectional LSTM, right? Not leveraging the contextuality or the transformer nature of this model, but rather just seeing it as being a static one where we have one representation for each word type. This is not work that we did, but work that others did using Latin BERT after our work came out. We only examined part-of-speech tagging as being this kind of morphosyntactic problem in the context of Latin. Others used it to try to train syntactic parsers as well. And again, find that when you treat a model that has Latin BERT as being the representation for each of those words in the sentence you're trying to parse, you can also get a state-of-the-art by virtue of having that increased representation. So I'll point you to work by Unic and Helvig here for more details on that particular problem. Okay, so part-of-speech tagging and just looking at the kind of morphosyntactic information that's present latently within BERT is one case study. Another case study is to think about the ways in which we can use these kind of contextual language models for textual criticism that really is focusing on emendations. Right? Because as others have noted, right, in the context of other languages like ancient Greek, the structure of mass language modeling really does model that of textual reconstruction. Right, so we have a sentence where there is a word or several words missing, and what we want to do is figure out what that word is. Right? That is essentially what mass language modeling is doing. So in the context of other work that has built computational models for this, though, a lot of work really tries to do this in a synthetic context, right, where you know the entire truth of a document, and you pretend that a word is missing. Right? Because in that context, you know what the truth should be. You see that this word, say, exists. You know what that truth is, so what you can do is mask it out, pretend it doesn't exist, and see how well that model can reproduce it. But in that context there, it's not really clear if that's really realistic in terms of what a textual critic would be faced as a real challenging problem. Right? Because if you take a word and just mask it at random, it's relatively easy to find words like say in this context that are relatively easy. Right? We don't have a lot of debate about what that word should be. So to try to evaluate this in a more realistic context, what we did was try to find a number of examples where we do see a critical marker of an emendation in a text, right? Where there has been some judgment that's been made clear. The textual scholar who has recreated or tried to reconstruct what those missing terms were, right? So, Publius Romanus 3 times fought against the Carthaginians. What we want to be able to do is take these reconstructions, right? Take these particular maps that people have found to be challenging and see how well these models can predict those in this mass language context. So to find these, what we do is search the Latin library for these bracket orthographic signifiers, right? These conventions that note textual conjecture, and then measure how often Latin BERT is able to reconstruct that particular human judgment by an action. So we found 2,205 emendations, where from this set we excluded any 5-gram, right, 5 words in a row that also appeared in the BERT training data. Right? And to make this as fair as possible for our model, we don't want to know what the true answer should be from having seen it multiple times in our training data before. So we're not going to include any of those words that we've seen in our training data in that time of training. What we find here is that when we compare the accuracy of this mass language modeling approach to the scholarly reconstruction, right? So this judgment of terror in this particular example, where we know not the truth, but at least a judgment of a scholar about what that word likely is going to be, we find relatively high agreement in the top 1 word, right? So the single best prediction that the model makes agrees with that person 33% of the time. If we look at the top 10 predictions, they agree the truth, the word the human judged to be the right reconstruction is in the top 10 lists 62% of the time, and in the top 50 lists 74% of the time. So as others have shown, these kind of models, when they're trained with a mass language modeling objective, can be useful, at least theoretically, in the context here of this practice of textual emendation. And I'll point out too that when we look at the kind of mistakes that these models make, they also tend to be relatively not predictable, but understandable, right? So, in looking at a couple of examples here, we see the left context in the first column, the right context in the final column, the prediction that Latin BERT makes, along with the emendation that a scholar has judged to be the correct one in context. A couple of places here we can see that they agree, and the places where they don't agree, like in the second row here or in the fourth row, there are natural explanations, right? So for the last one here, we have different inflections for omnes and omnia, right? It gets the word correct, but the inflection wrong. And the context here of this one example of anno et mago qui blank punicobello cornelium consulum apud liberaris caverunt. Anno et mago who captured the consul Cornelius at Lipari in the blank Punic War. The prediction that Latin BERT makes is secundo with the highest probability, 41%, but primo and not a second, not too far off at the second place, at 38.5%. And part of the reason for this ambiguity here is the fact that anno and mago are both signifiers of participating in the Second Punic War. But this act of capturing the consul Cornelius at Lipari is an event that happened during the First Punic War, right? So there is some ambiguity here in the text itself as being uncertain about which Punic War is being referred to. So we see both predictions rising up among these probabilities, again, signified or elicited by these different signals in the text itself. Third case study that we carried out here was on word sense disambiguation, right? So word sense disambiguation is also related a little bit to this task of speech for Kuhn that I talked about earlier on, right? That there are some word forms that have multiple word senses, some of them that lead to morphosyntactic differences in the sentence in its entirety, like Kuhn, leading to a noun being in the ablative case, versus it being a subordinate conjunction that also would, dictate a different kind of sentential structure. But a lot of examples of words that have ambiguity or policity in their meaning, or having multiple different senses, don't lead to meaningful differences in the morphosyntactic structure of a sentence. So this example here for Wirum has many different meanings, right? It can be a generic man, it can refer to a husband, it can refer to a number of other things. So the task of word sense disambiguation is really one of trying to take a sentence in context, and for those contentful words, like Wirum in this case, predicting what is the correct sense from some fixed inventory of sentences. So we examined this here by first creating a new benchmark for word sense disambiguation in Latin by mining examples of word senses from the Lewis and Short dictionary. Right, so dictionary entry like the word in here describes many different senses, right, with different levels of granularity for this dictionary term. And within too, we have one that also relates to morphosyntactic variation, right? In here, when it's used to mean within, takes a noun in the ablative case, but when it's used to mean into, direction toward, it takes a word in the accusative case. So in that context, we do have a structure that exists among the word sense and what happens with the morphosyntactic structure of the rest of the sentence. But again, not all of these examples have that. So we mine these sense examples from Lewis and Short by looking at the two major senses for words, right? For all the words that exist within this dictionary, let's look at the two major senses, right? They're marked 1 and 2 typographically within this particular resource. And then extracted at least 10 example passages that are present within Lewis and Short as examples illustrating that particular sense. So for all of these sentences here that we see with sense 1 of the word in, we know that in here is sense 1, right? It means within and not direction into or toward. So we have ground truth now that we can use and then train a model and see how well it performs at this particular task. So what we did here was learn a separate model for each of these dictionary headwords. And in general, this is a few-shot learning scenario, right? Which means that we are trying to train a model where we don't have a lot of examples, right? Where in this context here, we have fewer than 24 training examples and 59% of these dictionary head words that we're trying to learn models of word senses from. So we compared a couple of different models. One, Latin BERT, a baseline that uses static word-to-vec embeddings trained in the same training set that we trained Latin BERT on, but just embedded within the structure of a bidirectional LSTM, and also compare this against random performance. So in this context here, we balance this entire data set so that a random guess would have exactly 50% accuracy at discriminating between sense 1 versus sense 2 for all of these individual words. When we took a static embedding and embedded that within a bidirectional LSTM, again, using some fraction of these 24 training examples, we get an accuracy of 67.3%. But if we use Latin BERT, we see, again, a really big difference here that corresponds to a new state-of-the-art for this particular task that we introduced of 75.4. So again, what these models have been really proven to do well in a number of different languages is capture what words mean in a particular context. And that really is exactly what word sense disambiguation is as a task, right? You have a word that's being used in a particular sentence. What is the particular thing that that word means in this sentence? What we're asking in many cases is what is that word sense that we see being embodied by this word in this particular example. Large language models tend to do this really well. We see Latin BERT does as well. I'll mention to you again that others have expanded on this work by fine-tuning Latin BERT, the same Latin BERT, on a larger data set from the Thesaurus Linguae Latinae, and have also great results, better results than the ones that we report, because the TLL has a much bigger collection of example sentences, a different kind of sense inventory, so it's able, again, to learn from more data to learn these kind of finer sense distinctions as well. I point you to the work by Lenvine and Wick to see more about this particular expansion of this idea of word sense disambiguation using Latin. Okay, I'll close to with one more speculative case study, right, that captures the possibility or the promise, I suppose, of these kinds of models to capture connections that exist between text. Right, a lot of people have been working on this, specifically in the context of Latin and Greek over the past 10 years, pointing in particular to work by Neil Coffey and his collaborators with Tesselway. As one example of work that's really trying to use these kind of digital methods to explore how we can surface the connections that exist between texts. Because there's a lot of connections that we can think about trying to uncover that capture different kinds of representation linguistically, right? Not just between one language, but between multiple languages potentially, right? So one of my favorite examples here is of illustrating this is Ovid's use here of intertextuality, his embodiment of this idea when he's starting out the Amores by saying, "Arvo gravi numero violentaque bella parama." Right, I was going to speak about arms and violent wars and a heavy meter, but then Cupid came along and stole one of the metrical feet that turned it into an elegiac couplet, like the language of love poetry. But it's clear here that this is referencing the very first line of Virgil's Aeneid, right? Arma rorum quod cano, right? Both in terms of the lexical words, right? Arma is here, it's in terms of the meter, it's in terms of the syntactic structure. We see a lot of similarities that exist between these two lines. But this kind of intersectionality is also one that, of course, crosses languages as well, right? So even just thinking across languages between English and Latin, we see lots of examples from Milton's Paradise Lost, right? So whose midnight revels by forest cider fountain, some belated peasant sees or dreams he sees, while overhead the moon sits arbitress, right? Clearly an evocation here of Virgil's line from the Aeneid, right, as one who sees or thinks he sees the moon rising in the early month, right? Exactly not the same syntactically, but still enough similarity in knowing Milton's background, right? It's clear that there's a lot of connections here between these two works. And we can also think about the kind of intertextuality that exists beyond the lexical level, beyond the multilingual level, even simply at the level of the sound, right, the meter between these different texts. So Joyce's Ulysses famously starts with this line, right? Stately plump Buck Mulligan came from the stairhead bearing. Ulysses is clearly about the Odyssey, really structured around the story itself. But others have argued how even this line is itself a spondaic example, right? Again, evoking the same kind of epic meter that we see Homer's Odyssey being, right? right? So there's intersectionality here that we can think about across these different dimensions. But how Latin BERT might be able to approach some, or at least provide some kind of mechanism for interrogating this kind of intersectionality, really again speaks to its own use of encoding the meaning of words as they appear in context. Right, so because we have a 768 dimensional vector, a vector that corresponds to every word in each sentence, we can start asking questions about which words have similar representations, right, when we see them being used in very different senses by different authors. So if we look here for one example, I'll give you two examples here on this slide and the next slide. Right, so Gallia, Solmus, Divisa, and Partes Tres, right, this representation, when we look for the representation of the word in, from this sentence, the 768 numbers that we get from BERT that encode the meaning of this term in this context, and then ask from a big collection of text, all of the text that exists within the Latin library, what are the representations of the other words in any sentence that are most similar to those 768 numbers? The words that are most similar are other instances of the word in, but in contexts that are very similar. Right, so in all of these contexts where something is being divided into multiple parts, right? So divisus in partes tris, dividuntur in duas partes, divis in partes tres, quatuor partes divises, dividitur in duas provincias. Again, all of these are something that's being divided into multiple other things. So this here we can think about as giving us some kind of machinery for capturing this, at least theoretical idea of intertextuality. It becomes a little more clear when we take it from, use an example of a line that's much more widely quoted in Latin literature, right? This line, audentes fortuna iuat, right? Again, take this word audentes, run it through Latin BERT to get a representation for this word, audentes, and then find what other words have a similar representation in any other text in the Latin library. The other ones, tend to be very similar, right? So audentes forsque deusque iuat, audentes fortuna iuat, all the way down to the very last one here, again from Virginia, that's the same form, but just orthographically slightly different. So there's a lot of potential here too, and I think this is the area that I'm most excited by the use of these kind of contextual language models for doing something entirely new that older models like Wurtzbach and Blah or other models that have been using machine learning for doing NLP things in the digital humanities just have not been able to do with really high accuracy yet. But I think there's a lot of potential, at least for these models, to learn to capture some representation of what words mean in context that make this kind of intertextuality determination a natural thing to use them for, to uncover with more success than we've had. So anyway, I want to at least give you a sense about what Latin BERT is, motivated with this core idea of it being a language model and it really embodying this notion of contextuality. And then also talk about some of the case studies that we covered in the context of our work. But I'd encourage anyone who wants to know more to either go and read the full paper on arXiv or to just download the model and play around with it yourself. All of it is open source and available for anybody to use. So I'm happy to take any questions. Thanks.
Okay, thank you so much, David. I thought that was absolutely brilliant and really, really fascinating. I guess I'll start opening the floor for questions. Is there anyone in the room who wants to ask something to start? Yeah, go ahead.
Hi, thank you very much for the presentation. So I wanted to ask you, given that BERT has been trained over a very large training data set, and given that Latin evolves in time, how does BERT handles the language change?
Yeah, so, when I talk about to answer that question, let me put this in context. One of the rationales for moving from a static model to a contextual one is that when you have multiple senses of a word that you're trying to encode in one vector, what ends up happening is that the representation gets pulled between all of the senses, right? So a word like bear here, the representation for that would live somewhere between the animal bear and the football player bear, which is not ideal, right? You want to have more fine-grained representation that capture each of those sentences. In the context of larger language models, I think we can still think about this as implicitly happening, right? When you have 2,000 years in which we see a language being attested, and an evolution that or a change that happens in the context of a language over that entire time frame, we might see a similar kind of averaging effect that happens in the representations. Now, I think that there's a question here, though, in terms of the context of the sentence providing enough of a signal as to what period of Latin that is being used in, that it can actually provide enough of that implicit disambiguation that we don't have to worry about this averaging effect. I say this because I and my students have been looking at this question for contextual language models with other aspects of metadata, right? Say, if you train a language model, how much does it help to include information about the source, right? About who the speaker was, right? Whether it's a historical time, like the year in which a document exists, or a subreddit, right? Where, which community in Reddit do we see a language model or a speaker coming from that we want to encode? Does that actually help in the kinds of things that you want to do with that language model? Or is the context enough sufficient to actually know what the year was or what the subreddit was? And for all of our experiments, it really, the context of the sentence does encode enough that we don't need to actually know much about the metadata. So it's possible here in the context of the difference between Neo-Latin and Classical Latin that a similar thing would happen, right? Or between the works of Thomas Aquinas and Virgil, that they just look like different things. When you run them each through a different sentence, there's enough Thomistic signals in the sentence that we know that Deus means something very different for him than it did for Virgil.
But does BERT know where the text that is trying to recover come from, which kind of material as well?
It doesn't know.
Does it know this information? Because sometimes, from my personal experience in looking to inscriptions and papyri, it's relevant to know, what kind of text you are trying to restore, where they come from, also because the language obviously changes, documentary papyri use a different language from literary papyri, for instance. And the epigraphy from Italy is different from the epigraphy from Gaul. So I'm wondering whether BERT takes into account these variables when looking at the training data set that needs to use to fetch the linguistic information, because I think this might be relevant. You know what I mean?
Yeah, absolutely. So the question here is, does BERT have any information about the source of the documents beyond just the individual words or what the internals of the document, what those words are? And the answer is no, right? It only has access to the words themselves and not to any metadata about any document. And I guess what I'm getting at with my early response is that I wonder for some tasks if there is actually enough signal even if you don't know that this document came from Rome versus another document came from France, if there's enough signal in the language that it is implicit as not an external variable that you use to train the model, but it would be reconstructible. So again, if you wanted to, this I think would be an interesting case study to test this, if you could use these models themselves to do the same study I did for Coombe, and just simply take a bunch of collections from, it's an ethnographic collection from Rome, an ethnographic collection from a different place, and then do the same dimensionality reduction to see if we see the same separation. I wonder if it would be the same.
Yeah, I think it's interesting to look at it, yes. Thank you very much.
Okay, I think we've got quite a few questions in the chat. Let me just see. I think the earliest question we've got from Jack, he's asking, would it be advantageous for subtokens to be more equivalent to morphemes?
Yeah, I think it would. So I think the answer to that question is complicated because yes, I think ideally it would if we could do it right. Right, because morphemes do contain a lot of information, a lot of important structure that is important for the representation of higher order structure that you want to build on top of it, right? So for parts of speech, for syntax, for semantics, it really does matter. The challenge though is that when you introduce a morphemic kind of tokenization, it means that you have to have a really good morpheme tokenizer, right? And so if it makes mistakes, then those mistakes propagate to everything else downstream. I haven't done the study in the context of Latin BERTs. I would be curious to know if others have explored this, to see if those errors in tokenization, like a morphemic tokenization, actually matter for the kinds of things that you would want to do with one of these models. Because it might not, but that's the risk that comes up in my mind. It would be great if we could do it well, but I'm not sure we could do it well.
I think we've got a few more questions here as well. We've got a question, how can we potentially use Latin BERT to look at meaning change across time?
Yeah, meaning change across time. That's a great question. So there's been a lot of work looking at this in the context of static embeddings in the broader NLP and digital humanities community, right? So the idea with static embeddings has been, you take some snapshots of time, right? Some windows of, say, a decade, and you look at the representation for a word there, you do some kind of alignment between representation spaces and different time slices, assuming you train different models on each of those, and then just chart how a word becomes closer to a new set of nearest neighbors than it did early on. I think this kind of work is a lot easier with contextual models, right? Because essentially what you just need to do is run each of the sentences through the contextual model. And I'm being generic about this because it's irrelevant. You can use this for Latin, you can do this for Latin BERT, but you can do this for really any language from any of the BERT models that you see in those repositories in Hugging Face or elsewhere, where you just run the sentence through the model, you get the representation for the word that you're looking for, and you can calculate the nearest neighbors for just that specific instantiation of the word. And if you know that word was uttered in 1913, and the nearest neighbors for that instantiation are different from the ones in 2013, you have some elements of language change, where you can use the same sort of statistical machinery that others have used in the past for static embeddings to test the significance of that difference. But the process is a lot simpler because you have a representation for every mention of that word in any document for any time period. And you can calculate those nearest neighbors from that particular mention. So in a sense, I think it becomes, you use a bigger model, a more complex model, a slower model, but it becomes a lot easier conceptually, I think, to capture that kind of change.
Excellent, that's really, really cool. I think we'll maybe take the next two questions together and combine them with one of my own as well.
Right.
There's been a general question about how do you clean the text in the corpus, because spelling sometimes vary, especially replacing U with V and that kind of thing. And I'm also thinking of medieval Latin is often heavily abbreviated.
Yeah.
And how do you deal with things when things are not totally spelled out, or in the case of, I guess again, kind of emendations, and when things are missing, sometimes there are multiple versions of how an abbreviation can be interpreted and spelled out. So how do you handle that?
Yeah, it's a great question. I think people have chosen to do this in different ways as they train models on a big collection of data, some of which is noisy. Right, one strategy is to try to normalize it. Right, say let's use the same vocabulary, the same kind of spelling for those words that we treat as being canonical, where the data becomes clean and mapped to that form, and we learn our language model from that normalized text. With our model here, we made a choice to not do any of that normalization because doing the normalization means that whenever you want to run a model on some new data, you have to do exactly the same normalization process on that new data in order for that model to work on it, right? It expects the input to be in exactly the same format as whatever data it's trained on. And in our case here, we really wanted to have a really diverse set of inputs to reflect the fact that people are going to run this model on a very wide array of data, right? Some of which is going to have some OCR mistakes, right? Some of it's going to be in medieval, it's going to have some complicated abbreviations that you're not going to see in a classical text. And so to try to prefer to make it as general as possible, we wanted all of that noise up to a certain point, right? So, which is why we still did a process to filter out those documents that had so many OCR mistakes that it wouldn't really be beneficial for increasing the robustness beyond just adding way too much noise. But still, the principle is one where if the data is a little bit noisy, it gives you at least some capacity for building a model that's robust to the noise that really does exist in the documents that people are running on.
Right, excellent. I think that does kind of cover that other question about is it possible or desirable for there to be some kind of human editing involved in that.
Mm-hmm.
It's a really interesting point. And if I can follow up with that, exactly how big a corpus do you need to build a contextual language model?
Yeah, that's a good, great question. I don't know the answer to that. And there are expensive experiments to run to find out the answer, because it does require training the same model many different times and different subsets of the data to find out that answer. I know others have tried building it for ancient Greek or have run into problems because there is not as much cleanish Greek data available as there is for Latin. And so there is some number between 30 million tokens and 600 million tokens that seems to be the sweet spot, or not the sweet spot, but the critical spot of having enough size. There is a lot of work now going on in trying to distill bigger models into smaller models that can run on cell phones or in lower resource-intensive environments. But even those kind of models, they require starting out with a lot of data to learn them. It may just mean, though, that if you have less data, you learn a smaller model, and you don't try to learn a big one that's as big as 768 dimensions with 12 layers and 8 attention heads or so on. You can learn a model that has 100 dimensions and only 4 layers, and that might be the right size for what data you have.
Right, excellent. That's very encouraging for anyone who's like me, who's working on languages that have very small kind of corpora attached to them.
Yeah. Well, the other idea too is that a lot of the way that this works too is that you can train a model on a big collection of data and then adapt it to a specific domain, right? So if we want to have a model and people have tried this for ancient Greek too, right? There's a lot more data that exists for modern Greek. You can train a language model on that and then fine tune it to the smaller collection of ancient Greek. The two languages are very different at this point, so I don't know if there's been a lot of success for that, but there would be more success in taking a model like Latin BERT and fine-tuning it for, a smaller domain from a particular time period that you wanted to really perform really well on. That might be worth doing.
Excellent. I think we've got one more question in the chat, but before we go to that, I've neglected the room a bit. Are there any questions?
I just wanted to follow up with Marco, what Marco asked before. So I think what he discussed in this topic is particularly relevant when we come to text reconstruction.
Mm-hmm.
Because I'm thinking, for example, on Phil Sommershoot's e-type project, calligraphy.
Mm-hmm.
So when you have to reconstruct something and the model has been trained on every kind of Latin, that probably can be maybe challenging and it can lead maybe to mistakes as well. No?
Mm-hmm. Yeah. I mean, I think that way of doing that epigraphic reconstruction is right? It's not just the text that you have information on, right? You're marshalling a lot of other sources of information and making these judgments about what those words are. So the use of mass language modeling alone, I think, is not always going to be sufficient for this kind of scholarly practice, where it does make sense, of course, to include those factors into the decision. Whether they need to be in the model itself that you learn, I think is a separate question.
And then in the chat again, we've got Helma asking, is your basic unit of analysis the sentence? And then she also wants to kind of know what possible downsides are there to using the sentence as a unit of analysis.
Yeah, so I think this is also one of my I don't know how yours, but one of my myths I like to pick too. A lot of work in NLP focuses on the sentence as being the atomic unit, right? So for part of speech tagging, for syntactic parsing, all of the benchmarks essentially just take the sentence, trying to figure out the right syntactic parse for that, and then evaluate on that parse, where we know that there's a much bigger context the sentence exists in that likely provides a lot of information that can be useful. Right, for syntax, maybe less so, but it's definitely true for things like name entity recognition, which is also evaluated at the sentence level. So in this context, we evaluated part-of-speech tagging at the sentence just for this case study, but it's not one that is implicit within BERT by design. Not at all. It would have been just as easy for us, well, not just as easy. We could also have passed in an entire document up to 512 tokens and assess the part of speech or the word sense for that longer context if one existed. And I think also in the context of, the bigger future I see for this kind of work for, finding instances of intertextuality, then that context certainly does not need to be bound. There would be no reason to bind it to an individual sentence. You could use it for as much of a document context that you want to treat as potentially being elusive or intertextual in some way. So yeah, I see a lot of downsides for operating at the sentence level for a lot of traditional NLP tasks when we know that there are a number of other sources of information beyond the sentence that are important for a number of tasks that we want to use them for. And again, that's not built into Latin BERT. The one restriction that is built into it is a context length of 512 word piece tokens, right? So if you want to run a genre classification model, or to take some of Patrick Byrne's work, just differentiating between poetry and I think it was drama. To make a distinction, a classification for some document, then there are a number of hoops you have to jump through to be able to aggregate information from 512 word long chunks to make a decision about a document that's comprised of many of those chunks. That is a problem that bigger models like Longformer and some of the GPT models have been getting around by increasing that context length. But still, the idea of some fixed window that is a maximum number of tokens that you can have is still implicit to any of these models. And in some problems, we've often found logistic regression, which doesn't need to be bound by those length limits to perform better for some tasks in English, when you don't have to be restricted to that size. So yes, I completely agree with you, Noma, about sentences not being the right way to interpret.
I suppose that also gives you the flexibility if you want to look into smaller context as well. I find sometimes in poetry the line.
Oh yeah, absolutely.
It's sometimes a bit more valuable to work with.
Sure.
So then that also kind of links into things, differences with genre, maybe also the issues of medium that Michael brought up before. That might be a way to kind of be flexible and get around that or represent it in some way.
Yeah.
I'm just going to see if there are any more questions in the.
One you too.
Let's see. Oh, Gabby, go ahead.
So this is, I'm not sure whether this is a naive question or a thought experiment. I'm hoping it's somewhere in between. But I'm explicitly asking this as someone who's never worked with LLMs or CLMs. But going back right to your very first example, the redacted parts, and I'm thinking through the process that I would go through in trying to reconstruct that, and I'm wondering how that relates to the process that the BERT or the other LLM would go through in trying to fill that gap. Because my first thought was, yes, obviously you're expecting to see bark, but my second thought, just not far behind, would be something like the Sergeant Major bark, right? No other person barks, but sergeants bark.
Yeah, sure.
And then the third choice would probably be seal, because that's the other animal that barks.
Yep.
And maybe a few other animals, but not many. And with that sentence out of context, they'd probably be in that sort of order of probability.
Yeah.
But the kind of context which would enable me to guess a little bit more would be if there's any speech immediately before it, then it's probably gone back to being a Sergeant Major, right? Because that will barks words, and the others just bark intransitively.
Yep.
And then other things that would give a clue would be whether this is a naval scene or set at SeaWorld or something like this, and other kinds of things like that would give me clues on that. How is what I've just described different from what BERT does when it's trying to guess how to fill that word, or it's giving different probabilities in its list? Right?
Yeah, I don't think it's different at all. right? I think all of these define context. The context and overall use, this kind of big page diamond in a sense, right? That the more information you can use to narrow the context, the sharper the probabilities are going to be for the word that, I don't want to say you as a human, but that would appear in a naturalistic example of that sentence in a real context. So if we have a sentence like I gave, right, the blank barked, it is true that many different things could fill that spot. It may be also true that the prior probability is that it is mostly sentences of dogs barking that we're going to actually see. And in the absence of other information about agency or humanness, right, of speech or about other kind of volitional actions, it wouldn't predict sergeant major unless it sees those. But if it does, right, if we do see a sentence that has that broader and more precise context, I should say, I would expect to see those probabilities for those terms to reflect that. So I tend to be agnostic about the process by which any of these models do or learn anything. But I think that would be, I think that what we can say is if we look at the behavior of those models, what they would actually predict, what would those probabilities would be, I would predict that that would be the case. They would get sharper the more context that becomes more precise.
And so that's context both of the words around it, but also metadata. If you know we're based on a corpus of war novels and cop novels, then again the sergeant starts to creep back up yours. Yeah.
Yes, exactly. And so again, it's going to reflect the kind of biases and the kind of statistical tendency that exists in the data. So if it is mostly war that you're trained on, then yes, sergeant will be a priori more likely. But yes, however you define that kind of context, the more of it you provide, the more precise you should predict.
Is the model sensitive to things like sounds? So kind of going back to your Ulysses example with the metrical kind of similarity, but also with the BERT example, something else that I kind of thought of was, it's not appropriate at all given the structure, but I thought a bit of tree, because trees have BERT and that kind of thing. Obviously in terms of the syntax, that does not work, but always in my mind, I'm also thinking about what things sound like and synonyms, homonyms, all that kind of thing. Is the model at all sensitive to those kinds of associations?
That's a great question. I guess the question would be if they would be predictable as a kind of language modeling task. Like, could you predict the sound of, I guess in this context, like for the Ulysses context here, it was the meter that you would be predicting. I don't know if these models really do that well at that kind of metrical information. At the same time, though, there is, if you look at how the GPT models now, and ChatGPT and GPT-4 in particular, do with, constructing like fictitious rap patterns, right? They do obey that kind of form in a way that you wouldn't expect that they should be able to know about without in attendance to the kind of sonic elements. But part of that is just that the sound is often reflected in the lexicon as well, right? The choice of the words, and in particular in the subword token, so that words that rhyme end up having the same kind of subword tokens within them that end those words. And again, the kind of explicit structure that exists where you see that ends of lines tend to have a similarity in terms of their alternations in ways that are often predictable in the same way that other kinds of linguistic structure also is.
That's really fascinating. I think we've got another question in the chat.
Great.
Where, yes, have you thought about what other biases there might be with the data BERT has been trained on?
Yeah. So again, the data is coming to us from classical era, from Thomas Aquinas, from everything in the Latin library, and everything is kind of undifferentiated mass that's been published in books that exist in the public domain on the Internet Archive, right? And so I think there's a lot of uncertainty about what is actually in that collection, right? I mean, I jokingly said it could be, a lot of 19th century German dissertations on everything, a lot of scientific things as well, for whatever anyone did a PhD on, you could potentially see present within that kind of data. My guess is that a lot of it is going to be reproductions of classical materials, right? Of the classical texts, lots of Caesar, lots of Cicero, lots of Virgil and Ovid, that something get republished multiple times, that we often see in different forms with different kind of orthographies and different OCR levels of mistakes. So if I were to think about the kind of biases that exist, it would be more toward what gets republished many times. I mean, they always end up being tied to important questions about the values of these kinds of systems too, and whose perspectives that we're actually encoding and learning these representations from. I think there's more work to be done in understanding the consequences of that representation within the behavior of what Latin BERT does. But yeah, I think a lot of that often is designed around specific tasks. So again, if we're interested in understanding how Latin BERT reflects a particular gender bias, for example, for a particular question in assigning authorship or agency to characters in stories that are written in Latin, I think that would be an interesting tangible question to try to investigate that impact of what that data is on that specific question. I think I'd want to start from the question first and then interrogate what that bias is that leads to disparities in what we would expect in terms of the behavior of it. It was a great question.
I mean, I guess from the point of view of perception, I mean, there's always been this kind of bias that who are the great, classical authors to be reading.
Mm-hmm.
So in a way, I actually would want that bias in there and to represent kind of this is the kind of thing that people have kind of enshrined. This is the impression of Latin that has been passed down, and that people were very much trying to mimic when they were, trying to reconstruct Latin and trying to make medieval Latin even more like classical and trying to find all of those classical terms. So in a way, I think the bias has a historical significance that's maybe important that we understand, that we acknowledge. Whereas by contrast, we don't necessarily want that same sort of bias in ChatGPT, which we're using today, because then it will keep on kind of instilling that bias and perpetuating it.
Yeah, I mean, I can see that point for some kind of questions where the prioritization of the canon really does matter. But I think even the basic fact of just knowing what's in the data at a more fine-grained level would be good for giving people the levers for knowing whether or not that's appropriate for the questions that they're asking. Right? Or even just of saying that if you choose to debias these models, right, in the way that others have been doing for other language models in NLP over the past couple of years, interrogating how you can do that by fine-tuning it toward a different data set, or if there's a particular kind of bias that needs to be alleviated, like for gender in particular, devising a kind of test for doing that, I think would also be important as well.
Absolutely. Do we have any more questions in the room? Or? I think the questions on chat have also all been answered. So I think I'll take this moment to again really thank you, David. This was fascinating. It's giving me loads of ideas. I think that the chat has been very lively in kind of discussing some of the questions and appreciating your answers as well. I think everyone's really enjoyed this and given them a lot of food for thought. And thank you all online for joining us and being, contributing such great questions, especially since we're a bit thin on the ground in the room today. So you've more than helped sort of amend that for us. So thank you.
Thanks, everyone.